All right, so almost done. Look at we're celebrating. We're celebrating. We've got a few more sections to go over, and then we are completely done with AP statistics. So we are moving on to section 2 of Unit 8. Still looking at our chi-square test, but we are looking at the chi-square test of homogeneity. Okay, so kind of looking to see if things are similar or not. Okay, so comparing proportions. We use like a two proportion Z procedure or T procedure when we're looking at one or two populations, okay, and comparing them and seeing if there is any similarity between them. But what if we end up having more than just the one or two categories? The tests that we have used in the past, we can't really do it with any more than just two populations. So this is where the chi-squares of homogeneity comes in, because you can use it with many different groups and different ways of looking at a single population or multiple populations. Okay, and this is where we use our chi-square tests. Okay, so the overall test is to see if there's good evidence that there's any differences in the parameters that we're comparing. So we're looking at, okay, you have these, is there a difference in their averages? Okay, or are they the same? Okay, they should be the same no matter what, but this one being treated in one way is going to change a little bit. Okay, we will have some follow-up with these. Okay, so we'll have follow-up, which we kind of look at and go, okay, this is what's happening. And anytime that you, which we'll talk about this, but anytime that you reject the null hypothesis, you're going to want to follow it up and say this is why it is. A little bit further investigation into it. Okay, so again, your 4-step process: plan, state, do, conclude. So under your state, when you're naming your hypotheses, these are usually going to be written into words, not any symbols, because it's a lot easier to write it in words. Okay, so your null hypothesis is that there is no difference in the distributions of categorical variables of several populations and or treatments. And then the alternative is that there is a difference, okay, in the distribution. So you are looking and going, okay, is this distribution the same or are they different? And if they are different, then that means you are going to reject it. And that's what we want to see, is that if I do a treatment, or if I look at different populations, are there different distributions for them, or do they all follow the same? Okay, and again, write it in words. Symbols are a little iffy. Okay, so here's an example of which you would use it. Okay, so we have a store. A store is selling wine, and there are 3 categories of wine here. You have French wine, you have Italian wine, and you have other, which could be your South American wine, your Spanish wines, your California wines, anything like that. Japanese wines. So you have all your wines that fall under other. And so the idea was that if you played music, either French music or Italian music, would people more likely buy those type of wines? So if you're at a store and you hear Italian music play, are you more likely to buy an Italian wine? Or if you hear French music play, are you more likely to buy French wine compared to no music at all or just random music? Okay, and so these are your tables, and this is your two-way table that you have here. So down the horizontal, or down the vertical, we have our wines, your French, Italian, and other, and then along the top is the music that was played. So when no music was played, 30 French wines were bought, 11 Italian wines were bought, and 43 others. Okay. When French music was playing, 39 French, 1 Italian, 35 other, Italian 30, 19, and 35. So just by looking at this, you can already tell, like, that French category is pretty interesting there. And we're going to use statistics to try to prove that that falls into whatever we have. All right. So first thing we want to do is be able to find, or we state our null alternative hypotheses. And the null and alternative hypotheses in this case are that there is no difference between the distributions. That's our null, so there is no change. No matter what music you play, you still have the same amount of wine. The distribution for no music should be the same for Italian music and also for French music. They should all be the same. The alternative is that there is a difference, so that French or Italian music does make a change in people's purchasing. Okay, and that's what we're going to be looking at, and that's our alternative. Okay, so now finding the expected values. So finding the expected values in this case is slightly different from the previous one where we said this was the distribution, and we want to say it's uniform, or we want to say it's this or that. This one, you're going to be using the total values of each one. So you take the grand total from a row, multiply it by the total in that column, and divide it by the grand total. Okay. And divide it by the grand total number of wines that were taken. And you do that for every single box. Okay, so in this case, there would be 9 of them. And this is what it would look like. And this, again, falls under your step 2 with your planning, because you want to make sure that every single one is more than 5. Again, you're looking at the expected values, not the observed. Because if you look at the observed, one of them was less than 5. That doesn't matter because we're looking at expected. And the one that was 5, which was the French music and Italian wine, was 1. In this case, it's 9.6. So we're still over that 5 threshold. So you see here, so for no music in French, it was 84 under the none, and it was 99 for French. So you multiply those together, and then you divide it by whatever the grand total was of wine bought, which was 243. And you do that for all 9 of these categories to get their expecteds. Okay, so basically whichever box you want. So let's say we pick this middle one, French and Italian. Okay, French music, Italian wine. Okay, you look at the totals going down and over. The total over would be 31. The total down would be 75. You divide it by the grand total, and that's how you get your expecteds. Now, yes, this might seem like it's a giant pain in the tuchus, but your calculator is able to do this fairly quick as well. Okay, so just hold on. We'll go over how to do it on the calculator. Okay, formula, same formula as it was before. All your chi-squared tests are going to use the same formula. And because they all use the same formula, under the do step, you don't just state the formula that you're using, you state which test you're using, because you have to specify which test you're using. Okay, not just the formulas, because all 3 formulas all 3 tests use the same formula. But it's the same formula, observed minus the expected squared divided by the expected. If you want to find the p-value with this, once you know what the chi-squared is, you use chi-squared CDF on your calculator. Okay, it's under there. It's under the whole distribution test sections. But chi-squared CDF, you type in the chi-squared value, comma, E99, 1E99, and then you do your DF. And then once you have your degree of freedom, you can find what the p-value is. Now the degree of freedom here is slightly different from before, in which you have, instead of just counting how many categories you have, okay, and then subtracting by 1, you take the number of rows subtracted by 1 and the number of columns subtracted by 1, and then you multiply them together. So in this case, we had 3 rows and 3 columns, so that would be 3 minus 1, 2, 2 times 2, which means our degree of freedom in this example would be 4. Okay. So when you are writing out the equation, or writing out the math that you're doing, okay, you do not have to write out all 9 of them. If you do this little ... situation here, that tells you that you continue on the pattern. You just really have to do the first 2 and then, or 2 of them and then a third one, and just put the ... in between. And they're making the assumption that yes, you are adding them all together. You can use your calculator. If you don't want to use your calculator to add them all together, you can write them all out and do it that way. But this calculated chi-squared value got you an 18.28. The degree of freedom was 4, which puts the p-value at 0.01. Oh, 001, not just 0.101, 001. because the p-value is so low, and because it is basically 0.1%, we would reject the HO, which states that we do have convincing evidence that there is a difference between the distributions of the wine, which essentially means that the type of music that played did have an effect on people's purchasing powers. If you apply it back to the application, we would say we have convincing evidence of that. Now, because of that, we would have to go and do our follow-up with it. Okay, so quick summary of your 4 steps. So step 1, state your null and alternative hypotheses. You basically write out and you say that there is no difference in the distribution, and that there is a difference in the distribution for your null and alternative. Your plan: the expected value is more than 5. You can name the random and the independent ones, but they're not mandatory for these. For the chi-squareds, you just need to show that the expected values are more than 5. And once you have that, you're good with your plan, showing that it's normal. Next thing you would say, or you'd have, is your do, in which you want to state which test you're doing. Okay, so you would say the chi-squared tests the homogeneity, and then have your show your work, show the p-value, show the chi-squared value, show the df, and all that. Okay, so show those key things with it, but you got to name the test because the formulas are all the same. So you can't just say this is the formula I'm working with and moving on. You have to name the test itself. And then last, conclude, compare your p-value with the level of significance if it's given, or you would compare it if it's not given, then you would just say this is what it is. Okay. And then if you do reject, you have to do some follow-up analysis. Okay, so if you reject the null hypothesis, you need to do some extra analysis, and sometimes you'll be given a table that you can see the chi-squared values, and sometimes you'll have to use the chi-squared values yourself, which again we will look at on calculator of how to do that. And what we're looking for is any unusually large chi-squared numbers. Okay, so in the previous section, we had an example where one had a 7 point something. That would be extremely large. That would be the one that we'd point out and say, hey, this is where it's going to be a little strange there. Okay, but that's what we're looking for, is any large chi-squared values. Sometimes you'll be given a mini table. This is a mini table over here, and so it tells you what the actual values were. Next one below that is the expected values, and then the bottom one is the chi-squared values for them. And you see that 2 are highlighted. Those 2 are a lot larger than all the other ones, and so those would be the ones that you'd want to point out and say, hey, when the French music was playing, the Italian wine was a lot lower in this case. Or when the Italian wine was, or the Italian music was playing, the Italian wine was more likely to be bought. So it seems like the Italian wine is more affected by music than any of the other ones. Because if you look at all the other ones, they're all, 2, 3 is usually pretty okay. If you get any higher than that, that's where you've got some unusualness in there. And that's how you can help identify, oh, these are the ones that don't fit the distribution. And in a table like this, for the most part, unless everything is kind of off by about the same, you're going to have, at least 2. Because in this example, if you had 31 total, it should be distributed around 11, 9, and 11. This one was split up 11, 1, and 19. So you see how 2 of them are way off. Okay. So that further analysis, so if you do reject, you just want to take a closer look for the chi-squareds, and it's usually for this large of a difference you can easily see. I mean, from the beginning of this one, we knew that, oh, that's where our mistake was going to be, or that's where the distribution change is going to be, because that Italian wine is so low at only 1. And you just want to specify that when you go through it. Okay. All right, so take a second. You guys can run through this example and see what you get. And then we'll run through it. So 5, 4, you can pause the video, 3, 2, 1. Okay, so looking at this one, it's looking at political parties and landline cell phone use. Okay, so basically it's asking, is there a difference between political party and use of either a cell phone or a landline. So basically, are older people more likely to be Republicans or Democrats, or is there no difference? Okay, so this is what we have. So you're going under our state. Okay, so you would say that there is no difference in the opinion of political party between cell phone and landline users, and the alternative is that there is a difference between them. Okay, so remember with this one, it's no difference for the alternative or for the null, and there is a difference for the alternative, and that's under your state section. Next up is your plan. Okay, so you want to show the expected counts. Make sure they're all more than 5. Here's the expected table on this one, and again it's taken by, so for, if we go back to the previous table, you would take 96 times 96 and divide it by 200 to get this one, to get the cell phone Democrat. The landline Democrat would be 96 times 104 divided by 200. Neither cell phone would be 42 times 96 all over 200, so on and so forth. So you do that for all of them and you get those numbers. And you see all of them are more than 5 each. Okay, so we're good. Moving on to the do. And so now the do, we do our do, which is you do the observed minus the expected squared divided by the expected, and you add them all up. And again, you can shorthand it, but you do want to mention your test, the chi-square test of homogeneity, and then you have a degree of freedom of 2 in this case because there are 2 columns, so minus 1 is 1, and 3 rows, minus 1 is 2. So 2 times 1 is 2. Gets you a 3.22. Your p-value was 0.2. That p-value was fairly large, so because it is so large, we would just say we failed to reject the HO. We do not have convincing evidence that there is a difference between the political party and the cell phone usage. So there's not enough convincing evidence of a difference in political party and the use of phones in this case. All right. Okay, so let's make this a little easier when we talk about calculators. So you can use a calculator to help you do some of this. And basically you're going to be using the matrix function on your calculator. Okay, so if you have a TI, you have a matrix function that is able to do this. You push second and then matrix, and then you go under edit. And then under edit, it's going to ask you to basically make the matrix. What's the dimensions of it? 3 by 2, 2 by 3, etc. The example that we just did would be when you type it in, you go rows by columns. So there's 3 rows and 2 columns. You'd go 3 by 2. And then you would type in every individual one into the first matrix. Okay. Once you have it for the first matrix, okay, make sure you do not put the totals amounts. Okay. Your calculator is already going to calculate the totals, so do not put the totals when you're doing these matrices. After you've typed it into the matrix A, okay, you push stat test, chi-squared test, C, chi-squared test, and then your calculator is going to ask you which one do you want your observed to be. You'd say matrix A. Which one do you want your expected to be in, which would be matrix B. And it probably is already sitting there. Go through, solve it, and then what's going to happen is that it's going to calculate it. It's going to give you your numbers, your p-value, your chi-squared, your df, all that stuff. It's going to tell you all those numbers. Okay. But what it's also going to do is it's also going to tell you the expected value. So it's going to tell you the expected table. So that means, little secret, you can use that for your step 2 under plan. You don't have to calculate it yourself. Since your calculator is able to do it, you can just skip the plan, let's say on a test or anything. You can skip the plan part until you get your number and then just copy that table down at the end. So you don't have to calculate it yourself. Okay? And then you can go, oh, it is more than 5 or less than 5. Okay? So when you do this, matrix B, which you can go back and look at, you just go back to second matrix edit, go down to B, push enter, and then you can pull up matrix B and see it. And you can see what the actual numbers are. Those are going to be your expected values, and you can use those. All right? Save time and money by switching to your calculator. All right. So that's the end of this section. Section 2, we've got one more section. Well, 2 more sections, I guess, but the last section is really a review. And then we are done. We've got one more test to go over, which is the chi-square test of association / independence.